Generally, when we think of finding the volume of a solid revolution, we think of one of two methods. We think of the disk method or the shell method. Those are the two methods. And for me personally, the disk method is what I like to use if I'm revolving a region about a horizontal line. While I find the shell method more convenient if I'm revolving a region around a vertical line. Now that's just a general statement. So let's look at the shell method and see how it works. Let's just think about a curve. I'll just draw a generic curve here. And let's suppose that I go over here, and what I want to do, and let me just define a region here. I've got this f of x here, and I've got a and b, and I've got y equals 0. So I've got this region right here. This region bounded by y equals 0, y equals f of x equals a to x equals b. I've got this region here. And what I want to do is I want to take this region and revolve it about the y-axis so that I get a volume, so I get a solid, and I want to calculate that volume. Now you can picture what that might look like. It's going to kind of look like a skating board thing, you know, something the skating board people would use, right? You can see this solid. And let me start by just making a rectangle here. Now this rectangle has a width here of delta x, and I'll just say here's x. So the height here is f of x. Okay. Now imagine, if you will, if I take this rectangle and revolve it around the y-axis. Just think about that. You take this thing and you revolve it around the y-axis 360 degrees. What would you get? Well, you would get a cylinder, right? You would get a cylinder that has some thickness to it. The thickness would be delta x. Now let's just take a minute and draw what that might look like. We have the outside cylinder and the inside, okay? And then down here, let me just bring it down. And we have, and then down here. So we would have this hollow cylinder, right? Okay, a hollow cylinder. And it has some thickness to it. It has this thickness right here that's delta x. That's what we would get if we revolved this rectangle about the y-axis. Now think about what the area or the volume of this cylinder would be, this hollowed out cylinder. What would be the volume? Well, to get the volume, you would calculate 2 pi r times h. That would be the surface area of the cylinder, right? But then you have to multiply it by the thickness to get the volume. And the thickness there is delta x. That would be the volume of this cylinder. If we rotate, if we revolve this rectangle about the y-axis, we would get a volume, and this would be the way to calculate that volume. Now think about what would let's just see if we can figure out what these parts are. The 2 pi is just itself, and we've got the r. We'll come back to the r. But what about the h, the height? Well, the height is the f of x. And the thickness is, of course, delta x. Well, what is the radius? Well, think about the radius. Here is the origin, right here. Or not the origin, but the y-axis. And think about the distance over here. Well, the distance would just be x. I put x in the middle because remember what we're going to do is we're going to have this we're going to let delta x go to 0. So x would be the radius, see, from here to here. So x is the radius. So what we have here is we have 2 pi x f of x delta x. That would be the volume of that little hollow shell with a little bit of thickness. Now remember, if we let delta x go to 0, and if we do this for a lot of rectangles, millions and millions, an infinite number of rectangles, and then we add them all up, the way we let delta x go to 0, and we let the number of rectangles go to infinity. So in other words, if we let delta x go to 0, we're taking the limit of this Riemann sum, and we're getting this. We're getting 2 pi r, which is x, times the height, f of x, dx. So this is the way that we could add up that infinite number of those hollowed out shells. And when we add up all those, it forms a solid. And that solid, the volume is given by this, because each one of these is the solid of one of those shells, or is the volume of one of those shells. So the integral is what we use to add up all that stuff. That's what we're doing. So let's look at an example here. Let's suppose that we've got y equals 0, y equals x squared, x equals 0, x equals 1. Let's suppose we want to revolve that region about the y-axis. That's what we want to do. So when I see that I'm revolving about a vertical line, I think of the shell method. It's usually the easiest if we're revolving about a vertical line. So let's see how it would go. We got 2 pi. Okay, that's the first part. And then x, f of x. Well, f of x is x squared. And then dx from 0 to 1. Did we get everything? See, x, f of x, f of x, dx. Yeah, there it is. This should give us that volume that we're looking for. So let's see how this goes. This is 2 pi, the integral from 0 to 1 of x cubed. And that will give us 2 pi times, here we go, I'm going to go ahead and get the antiderivative. There we go. And that would be 2 pi times 1/4 times 1 to the 4th minus 1/4, 0 to the 4th, of course. We're just doing every single step here. And that would be 2 pi times 1/4. That's what that would work out to be. Or in other words, pi over 2. So what we've done there is we found that volume of that solid, the solid formed when we do that revolution. Yeah, so that's revolving it about the y-axis. So it's pretty straightforward, pretty simple when you have a problem like this. Okay, when it's just a simple region like this, it's not too much trouble to do that computation. Now, let's suppose that we take that same region. Okay, so we've got y equals 0, y equals x squared, x equals 0, and x equals 1. And let's suppose that we want to revolve that not about the y-axis, but about a different line. Let's suppose we want to revolve it about x equals, let's say 2. Something like that. X equals 2. Okay, so let's see what the picture looks like here. Okay, so here I go. I've got the x squared there. And I'm going from 0 to 1. This is my region down here. And over here is x equals 2. X equals 2. So what I want to do now is I want to take this region right here and revolve it around this. So it's going to swing out here, right? It's going to be kind of a hollowed out thing, a hollowed out solid. So here's what we do. Since it's a vertical line, we think, okay, I'm going to do 2 pi. I'm going from 0 to 1. Now, I don't know what the radius is, so I've got to figure out what the radius is. Let's think of a very thin little rectangle here. let's suppose we've got this rectangle, and I'm going to bring it out and around the line y equals 2. What is this radius? Think about this cylinder formed here by this very thin, it's not very thick, right? It looks like a line. What would that radius be? Well, the radius is not going to be x. Think about this. The radius would be 2 if it went all the way back here, but it doesn't. It just goes to right here. Whatever this value for x is, right? So it's 2 minus this. What if this is 1/2? Then the radius is 2 minus 1/2, this. What if it's 1/4? Then the radius is 2 minus 1/4. See? So in other words, the radius is going to be 2 minus x, whatever x is, and then times x squared dx. So this is what I would integrate to get the solid form, the volume of the solid formed when we revolve around x equals 2. So if you wanted to see how are we going to integrate that, well, I would just distribute through. And then we get that. Okay, so now here's what we've got. We've got 2 pi, 0 to 1, 2x cubed, no, squared minus x cubed. Okay, I guess I didn't need to rewrite that. But here we go. So this is going to be 2 pi. Now here's the antiderivative. 2/3 x cubed, okay, minus 1/4 x to the 4th. And we're going from 0 to 1. Okay. Okay, now let's see what that's going to be. That's going to be 2 pi, 2/3 minus 1/4. Okay, now, and of course we would minus putting in a 0, but there's no point in that. So let's see what this would be. This would be, I'm going to factor out, I think, a 12 from here. So this would be 2 pi over 12. And let's see what's left in there now. If I factor out a 12, I would need an 8 here minus a 3. See? Now let's see if that works. If I multiply 8 times 1/12, I get 2/3, yep. And then if I multiply a 1/12 times this, I get a 1/4. Yeah, so that's it. So now this is pi over 6 times 5. So that would be 5 pi over 6. Okay, now let's use the same region now. And let's suppose, so we've got y equals 0, y equals x squared, x equals 0 to x equals 1. And now let's revolve about x equals -2. So let's try that one. So now here's what we have. Okay, so we've got our region here. Okay, there's 0 to 1. And we've got all this, and we're revolving that about this line, -2 over here. X equals -2. So let's think about just a general rectangle here. Here it is. This is a very thin little rectangle. We are going to take that, and we're going to swing it about y equals -2. So think about this. It swings wide out here. What is the radius going to be? Well, it's not going to be this length here, right? This length here is 2. We're going to add some to it, right? It's going to add this little bit here. So if this is x, our radius is going to be 2 plus x, right? So we've got this. We've got 2 pi, 0 to 1. Our radius is going to be 2 plus x. Then our height, and then dx. So this would be the integral that we have to deal with in finding that volume. Notice it's when we're revolving around x equals 2, it's 2 minus x. When we're revolving around x equals negative 2, it's 2 plus x. And then this is the integral that we would have to solve. Now let's look at another region. Let's suppose we've got y equals x squared and y equals the square root of x. And we want to revolve these about the y-axis. Okay, so what would be the setup on that? Well, if you look at this region, we've got y equals x squared, y equals the square root of x. Whoops. Didn't need to go back down. Square root of x, x squared. Now look, here's what I'm going to do. I'm going to say 2 pi. Now these intersect here at 0, 1. I mean, they intersect here at 0 and at 1. So our bounds of integration are 0, 1. If we couldn't see that obviously, we would just set these two equal and solve. But now, we've got the radius to be x. You know, we're revolving around the y-axis, so the radius is x. But what about the height? Well, the height is this right here. And that's going to be the top function minus the bottom function. There we go. That's the height. So the difference is when we've got a region like this defined by two curves this way, we have to remember, okay, I've got to find the height, and the height is not just the function value. It's going to be, we have to be a little more careful. So this would be the height, and this would be how we would get that solid if we're revolving around the y-axis. Now, if we're revolving around, let's suppose we're revolving about x equals 2. Well, here we go. We've got 2 pi, the integral from 0 to 1. Now our radius is going to change, right? It's going to be 2 minus x. But our height is the same. So the integral gets a little more challenging.